Welcome to my lecture series on group theory. Today we are going to discuss permutations. So first of all, we define what a permutation is. So the definition is here. A permutation of a finite set S is a one-to-one mapping or function from S to itself. And since S is finite, hence any one-to-one function from S to S will be onto, and hence permutations are bijections from a finite set S to itself. That is, a permutation maps each element of a finite set S to an element of the same set in such a way that each element of the set is used exactly once as an image. For example, we can illustrate this from this example. So here I have a set S. It consists of 4 elements, 1, 2, 3, 4. So here is S, 1, 2, 3, 4. Here is a mapping which is one-to-one from S to S and is defined in this way. 1 is mapped onto 4, 2 to 1, 3 to say 2, and 4 to 3. And since we can see that F is a one-to-one mapping from S to S, hence it is a permutation. Usually, the set S that we consider is this set up to n, where n is a natural number. And the elements of S being permuted are called symbols. So we usually call the elements of S as. How do we specify permutations? So in the previous example, we have seen that if we have a set S with only 4 elements, 1, 2, 3, 4. So for a permutation, using that notation, I have to write the elements of S again, and then I have to draw a line from each of the element to the elements of that set again. We look for a more convenient way of specifying this permutation. So, what do we do in this case? For example, I have a set S with n elements. What do? We write the elements of this set in a line. And then underneath this element 1, we write its image. Similarly, underneath this element 2, we write its image, and so on. So underneath each element of the set S, we write the image of that element, and we enclose this whole array into a bracket. And we call it the permutation. For example, if for this example we consider this representation, then what do? We write the elements of the set S in this first line. And then underneath 1, we write its image, and we see here that 1 is mapped onto 4. So underneath 1, we write its image 4. Similarly, 2 is mapped onto 1. Hence, underneath 2, we write its image 1. Underneath 3, we write its image, which is 2. And similarly, 3. Hence, this is a more convenient way of representing this permutation. Still, there is an issue that we have to write in this representation each element of the set twice. So we look for a more convenient way of representing this permutation. And how do we do it? Consider this permutation from a set S with 6 elements. So I have a permutation from a set with 6 elements. And what does it do? It maps 1 onto 5, then 2 to 6, 3 to 1, 4 to 2, 5 to 4, and 6 to 3. So, what this permutation does, it maps 1 to 5. We can see here that this permutation maps 1 to 5. Then in the next step, we look for the image of 5. So this is 5 and it is mapped onto 4. Hence, 5 is mapped onto 4 by this permutation. In the next step, we look for the image of 4 and 4 is mapped onto 2. So 4 is followed by 2. Similarly, in the next step, we look for the image of 2 under F. So the image of 2 under F is 6. Similarly, then we look for the image of 6, which is 3, and 3 is mapped back again to 1. Hence, this can be represented as 1 is mapped onto 5, 5 is mapped onto 4, 4 is mapped onto 2, 2 is mapped onto 6, 6 is mapped onto 3, and 3 is mapped back onto 1. And this representation is called the cycle representation of the permutation. And this representation that we have seen here, this is known as the two-line form of a permutation. And how do we represent this permutation in this case? We write F as, we start from 1, then 1 is mapped onto 5, 5 is mapped onto 4, 4 is mapped onto 2, 2 is mapped onto 6, 6 is mapped onto 3, and 3 is mapped back to 1. And hence we stop here. So here, 1 is mapped onto 5, 5 is mapped onto 4, onto 2, 2 to 6, 6 to 3, and 6 back to 1. Since the cycle has no starting point, hence this can equivalently be represented as, if you don't start from 1, we can start from, say for example, 4. So we can see that 4 is mapped onto 2, 2 is mapped onto 6, 6 is mapped onto 3, 3 is mapped onto 1, 1 is mapped onto 5, and 5 is mapped back onto 4. Hence we stop here. Or equivalently, we can start from any symbol. If we start from 3, so 3, 3 to 1, 1 to 5, 5 to 4, 4 to 2, 2 to 6, and 6 back to 3. But usually, if we have symbols, then it is more convenient to start with the smallest number. So if the symbols are numbers, then we start with the smallest number. The problem here is that not all permutations can be written in cycle form as simply as in our previous example. For example, if I consider this permutation 1, 2, 3, 4, 5, 6, 7, 8, and the images are here. 1 is mapped onto 4, 2 to 6, 3 to 8, 4 to 3, then 5 to 1, 2, 7, and 5. And here, if we start with 1, we can see that 1 is mapped onto 4. Then we look for the image of 4, and 4 is mapped onto 3 by this permutation G. So 4 is mapped onto 3. Then we look for the image of 3, which is mapped onto 8 by this permutation G. Then we look for the image of 8, which is mapped onto 5 by this permutation G, and 5 is mapped back onto 1. And hence the cycle representation here for this one would be 1 to 4, 4 to 3, 3 to 8, 8 to 5, and 5 to 1. But what about the elements 2, 6, and 7? So we start with element 2, and we can see that 2 is mapped onto 6. Here we can see that 2 is mapped onto 6, and 6 is, then we look for the image of 6, which is mapped back onto 2. Hence this is the cycle representation for this one is 2, 6. And the last one, 7, is mapped onto 7. Hence we write this as 7. And this whole permutation G can then be represented as 1, 4, 3, 8, 5, 2, 6, 7. Or in cycle representation 1 to 4, 4 to 3, 3 to 8, 8 to 5, and 5 back to 1. And this one can be represented as 2 to 6 and 6 back to 2. And this one can be represented as 7 is mapped onto itself. And in this case, we say that G is a product of disjoint cycles. And the disjoint cycles in the representation of G are 1, 4, 3, 8, 5. This is one cycle. Another cycle is 2, 6, and another cycle is 7. So here is the strategy, that how do we write a permutation in cycle form. So number 1, the strategy is this one. We choose any symbol. For example, if you are working with numbers, then we choose the smallest number, say 1. And what do? We find the image of 1. And then we find the image of this image. Hence, then we find the image of the image. Under this permutation, under the permutation F, and so on. Until we encounter the starting symbol, in this case 1. And what we should do, we should write these symbols as a cycle. And then the next step, repeat the process described in 1 with any symbol that has not yet been used. That has not yet in any cycle until all the elements of S have been placed in cycles. As an example, if we consider this permutation, then we start with symbol 1 and we find its image. So the image of 1 is 3. Then we look for the image of 3, which is 7. Then we look for the image of 7, which is 1. Hence, in cycle form, this can be written as 1, 3, 7. Now, we start with the symbol 2. So, 2, which is mapped onto 5. Then we look for the image of 5, which is 6. Then we look for the image of 6, which is 2. And hence, in cycle form, this can be written as 2, 5, 6. Then, we start with element 4 because 3 has already been placed in this cycle. So, we start with 4 and we see that 4 is mapped onto 8. And then we look for the image of 8, which is mapped onto 4. And hence, in cycle form, this can be represented as 4, 8. And in this case, this G can be written as a product of disjoint cycles is 1, 3, 7, 2, 5, 6, 4, 8. In a later video, we will see that these disjoint cycles will commute, and hence we will be able to write this as 2, 5, 6, 1, 3, 7, 4, 8. Or we can write this as 2, 5, 6, 4, 8, 1, 3, 7. We will see a theorem regarding this problem. Now we discuss the identity permutation. So it is a permutation of the set S that fixes every symbol. So for example, if I have a set S with 7 elements, then a permutation that fixes every element of this set is called the identity permutation, and it is usually denoted by E. In cycle form, we can represent this as 1 is fixed, 2 is fixed, 3, 4, 5, 6, 7. The problem here is that if we omit any cycle from this representation, then nothing is left. And hence, we have the following convention. What is the convention? When it is clear from the context, which set of symbols is being permuted, when we know about the set of symbols, then what we can do? we omit fixed symbols. For example, I have 1, 2, 3, 4, 1 to 1, say 2 to 3, 3 to 2, and 4 to 4. Hence, if I know that the set S in this case is 1, 2, 3, 4, the cycle representation of this permutation, say this is F, then the cycle representation is 1. We know that 2 to 3, 3 to 2, and 4. Hence, using our convention, we can omit, because we know that the symbols are 1, 2, 3, 4. Hence, this is 2, 3. And from here, it will be clear that 1 and 4 are fixed by this permutation. And this is the first one. The second one, when working with permutations in cycle form, we denote the identity permutation by E. Thank you.